This is my geometry course. Today we're going to prepare for test number 3. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. I mentioned when we prepared for tests 1 and 2 that there are some subjects where you can study an hour the night before and ace the test. But math doesn't work that way. You need at least 2 days to prepare for a math exam. But it doesn't matter how many times you tell students to study for a test, they're not going to do it. So in order to force you to do at least some studying, we're going to do a practice test right now together, and I'm going to give you a practice test for homework. And these tests are going to do 2 things. Number 1, like I said, they're going to force you to do a little bit of studying. And number 2, they're going to familiarize you with the test, so you can't say that the test caught you off guard. Now, be aware that doing these practice exams is not going to guarantee that you get an A when you take the test in the next class. But hopefully you'll at least pass the test. That's the point of these practice exams. Also, these tests are not optional. You must take these practice tests before taking test number 3 in the next class. So that said, let's get into it. Like all my tests, there's 25 problems, 4 points each for a total of 100 problems. A calculator will be useful for this test, so you're allowed to use a calculator. And for the test in the next class, and for homework. Now, as with all the practice tests, I want you to attempt each problem before you watch me do the problem. That way your mind is going to be much more engaged in what we're doing right now. And you're going to get a lot more out of this. So I want you to attempt this problem, see if you can do it. Now, if you can't do it, that's okay. If you forgot, that's fine. But don't just watch me do it. At least try to understand what the problem is asking and try to do it yourself. And then when you get stuck, you can start the video. So try number 1. And when you come back, we'll do it together. All right, we're back. So we have 3 sides of a triangle. First side is x, second side is 48, and third side is 31. You can order it differently. It doesn't really matter which way you order it. And remember, we learned a theorem called the triangle inequality theorem, which says that the sum of the lengths of 2 sides of a triangle must be greater than the length of the third side. That must be true for triangles, or else you cannot build a triangle with the side length. So what that means is that, I guess I'll use letters here, x plus 48 must be greater than 31. The sum of these 2 sides must be greater than the third side. But it's also true that the sum of these 2 sides, x and 31, must be greater than the third side, 48. Whoops, sorry. I keep going back to Roman numerals. And it's also true that the sum of 48 and 31 must be greater than the third side, x. So all of these inequalities must be true in order for the numbers to actually be able to develop a triangle. So let's solve this inequality. We're going to subtract 48 from both sides to solve the inequality because we want to isolate x, and we get negative 17. Now let's solve this inequality. Subtract 31 from both sides, and we get x is greater than 17. And then we'll solve this inequality. 48 plus 31 is 79. So x must be less than 79. So what we're going to do is we're going to ignore this one because this one doesn't really give us any useful information. Of course, x has to be greater than a negative number. It's possible for a side length of a triangle to be a negative number. So this inequality over here really doesn't do much for us. But these 2 inequalities, they give us useful information. X must be greater than 17 but it must be less than 79, and that's the answer that we're looking for. You can also say that x must be greater than 17 and x must be less than 79. You can write it either this way or this way. It doesn't really matter, but it's easier to write it in the more compact form. So if you didn't remember that, that's okay. That's the point of this test, is to go back and remember these things. And by the way, when you study for the test, I forgot to mention, when you study for the test, you need to go to the description sections of the videos and click on screenshots of classwork and take pictures of all that stuff, and that'll give you the guide in terms of what you need to study. So if you got that answer for 1, good job. So on to number 2. It says use the polygons below to answer problems 2 through 4. So we're going to use these polygons up here to answer these problems here. So we're going to show that the polygons are similar. And there's 2 things that we have to do to prove that 2 polygons are similar. We have to show that the corresponding angles are congruent. For example, these double arcs, they're congruent because they're both double arcs. And these single arcs are congruent because they're both single arcs, and so on and so forth. The second thing we have to do is show that the ratios of corresponding sides are all equal. So go ahead and try number 2. When you come back, we'll do it together. All right, we're back. So part A, we're just going to state that angle A is congruent to angle E. Angle B is congruent to angle F because they're both right angles. And in a formal proof, you'd have to use the right angle congruence theorem, but we're not doing a formal proof here. So we know that if they're both right angles, then obviously they're going to be congruent. I'm not going to make you use the right angle congruence theorem. Angle D is congruent to angle H because they're both single arcs. And angle C is congruent to angle G because they're both right angles. So that's the first thing that we need to show to prove that the polygons are similar. So now we go on to part B. We're going to show that ratios of corresponding sides are equal. So 16 divided by 24, and I use these 2 numbers here, 16 divided by 24, must be equal to 20 divided by 30. That's these 2 numbers here, which must be equal to 12 over 18, which is these 2 numbers here in purple, and that must be equal to 28 over 42, which is these 2 numbers in green. So we have to show that those ratios are all equal. We don't know that they're equal now. We can't really tell, but if you reduce, you get 2/3, 2/3, 2/3, and here you get 4/6, but that reduces to 2/3. So we can just reduce it further to 2/3. I got 4/6 by dividing both sides by 7. So as you can see, these ratios are all equal. So what we did is we proved that the yellow AD over HE is equal to the blue AB over EF, which is equal to the purple, the purple is BC over FG, which is equal to the green, which is DC over HG. We proved that the ratios of corresponding sides are all equal, so that's part of our answer. Really, this whole thing is part of our answer, but I'm just going to rectangle those last parts. So if you got that right, good job. So I just want to show where we got those values. You probably don't need me to do this, but I'm just going to make it clear where those came from. Okay, so on to number 3, write a similarity statement. Now, when you write a similarity statement, you can draw the picture if you want. Just draw like a hypothetical picture of that shape before you draw your letters, and then do your A, B, C, whatever you want to do. So go ahead and try number 3. When you come back, we'll do it together. All right, we're back. So I've got that polygon ABCD is similar to that same polygon. Again, your picture doesn't have to be perfect, but try your best. And we started at A. That's the double arc. You see up here? See up here in the double arc? All right, so we started at A, so we have to start at the double arc over here, which is E. Very important that you get the right order, or else your similarity statement is not going to be correct. So then we went from A to B, the right triangle, or excuse me, the right angle. So we have to go from E to F over here. So the next letter in our similarity statement is F, and then down to G and to H, and you get the point. Okay, so that's the answer for that one. So I'm going to rectangle that. So notice that I followed alphabetical order. If you want to make sure that your answer is correct, then please do alphabetical order, because there's actually many different ways that you can write that similarity statement. So your answer may have been a little bit different if you didn't start with A, B, C, D. Okay, so number 4, write the scale factor. See if you can do number 4, part 1, and when you come back, we'll do it together. All right, we're back. So the scale factor is the ratio of corresponding sides, and we already found that. It's up here, 2/3. So we can just write 2/3. You can also write 3/2. And that brings us to part 2 of this problem. It says write the scale factor in a different way. So what that means is just flip the scale factor and you can write it as 3/2. Now if you wrote 3/2 up here, then you would write 2/3 down here. This is just trying to show you that there's 2 ways to write a scale factor. So if you got that one, good job. I kind of did this one for you, I guess. On to number 5. Go ahead and try number 5. Again, if you can't do these, if you get stuck, that's okay. But think about the problem, think about what you can do, and when you come back, we'll try it together. All right, we're back. So reflecting about this dotted line means that you count how many spaces from a point to the line of reflection. In this case, it's 1 space. Then you count the same number of spaces across, and that's where you put your new dot. So our new dot would go here. Same thing here. You count 1 space to get to the line of reflection. So you go 1 space across the other side. If you're going to reflect this point here, then you count how many spaces to the line of reflection, and it looks like it's 4 spaces. So you go 4 spaces directly across to get the reflected point there. So that is C prime. And this is, oh whoops, that's not B, that's A prime. B prime and D prime. Very important that you label your reflections properly. It may be common to accidentally label this a B or this an A prime. So that is how to reflect. If you got that answer, good job. Try number 6, and when you come back, we'll do it together. All right, we're back. So we're going to dilate about the origin with a scale factor of 3. Now, if we dilate about a point that is not the origin, that's a lot more difficult. But dilating about the origin is actually pretty easy. First, let's label these points. So point E would be -1, 2, and point G would be 1, 0, and F is -1, -1. It's just easier for us to label those. And what we're going to do is, it says dilate about the origin with a scale factor of 3. So that all that means is we're going to multiply all these numbers by 3. So if you multiply this by 3, you get -3, 6. Multiply these coordinates by 3, and you get 3, 0. Multiply these coordinates by 3, and you get -3, -3. So now we're going to plot those new points. So -3, 6, 1, 2, 3, 1, 2, 3, 4, 5, 6. So that's right there, next to that 3. And 3, 0 would be here. And -3, -3. 1, 2, 3, 1, 2, 3 is there. And then we just connect the dots. So we kind of have to go through that G, but that's okay. And we need to label these points. So this is E prime and G prime and F prime. So that is a shape that's been dilated by a scale factor of 3. So if you dilate with a fraction, then it's actually going to make the triangle smaller. So good job if you got that one right. Again, if you're a little rusty on these, that's okay. You should be rusty because we haven't done this for, however long it's been since this class, a week or week and a half or 2 weeks or whatever. So now we're going to rotate -90 degrees about the origin. Now remember, in mathematics, a positive rotation measure is considered to be counterclockwise. You wouldn't think that that would be true, but it is. If you rotate counterclockwise, that's positive rotation. But if you are rotating a negative angle measure, then you're actually going clockwise. So -90 degrees means you're going to be rotating this way. And the easiest way to do this is to draw half of a rectangle. You can call this maybe like an axe or something. You're drawing some sort of a device where you, what do they call that? A pick or a plow or something like that. Then you rotate this down, and it's going to look like, well, I'll use a different color, so it'll be easier to see what we're doing. If you rotate it down, it's going to look like this. I'll use blue. If you rotate it down, it's going to look like this, you see. Sorry, those colors kind of blend in. So the new point is now here. So now we're going to do the same thing with K. Make a half rectangle shape, and then rotate that 90 degrees down, and you're going to end up with this. So then your new point is here. So let's start marking these before we forget. So this was M prime, and this was K prime, and down here would be L prime. You can kind of get a feel for what the shape is going to look like. You don't have to do that for every one. And then we've got our next point there. That's going to be N prime. So then we can connect the dots. So that was a 90-degree rotation in the negative direction. Again, clockwise is the negative direction and counterclockwise is positive. I know that seems strange, but that's just the way that they do it in mathematics. Okay, on to number 8. Go ahead and try number 8. When you come back, we'll do it together. All right, we're back. So remember, we learned the triangle inequality theorem that tells us the sum of the lengths of two sides of a triangle must be greater than the length of the third side of the triangle. So that means we're going to write three inequalities. We're going to say 8 plus 12 must be greater than 4, and 8 plus 4 must be greater than 12, and 12 plus 4 must be greater than 8. So if we add these together at the far left, we get 20 is greater than 4. That's definitely correct, right? Over here we get 12 is greater than 12. That's not correct. 12 is not greater than 12. It's equal to 12. So we already showed that it's not possible to make a triangle with these numbers. Let's go ahead and add these up. We get 16 is greater than 8. So what that means is that these check out. These work. But this one in the center, that doesn't work. That showed that we cannot make a triangle with these numbers. So the answer is no. And so we can rectangle all that. That's all part of our answer because it says write the inequality that shows it's not possible. And that's the inequality there. But it's not true that 12 is greater than 12. So we have to write a vertical line through the inequality saying that it's not greater than 12. So if you got that one right, good job. Number 9, it says circle each group that contains concurrent lines. You may need to circle more than one group. So go ahead and try number 9. When you come back, we'll do it together. All right, we're back. If lines are concurrent, that means there's 3 or more lines that intersect at the same point. Now these lines, they intersect, but there isn't 3 lines that intersect, 3 or more lines. This line intersects with this line, that's 2 lines. This line intersects with 2 lines, so on and so forth. Same thing here, and we don't have any intersecting lines here, but in this grouping, we have a bunch of lines that are all intersecting at the same point, so those are concurrent lines. So if you got that one right, good job. So on to number 10. Go ahead and try number 10. When you come back, we'll do it together. All right, we're back. We're going to use something called the triangle side inequality theorem, which tells us that if we look at the smallest angle in a triangle, the side opposite that angle is going to be the shortest side. And they want the shortest side first. So AC is going to be the shortest side. Then look at the angle that is the next biggest angle. And the side opposite that angle is going to be the next biggest side. So BC. And then, of course, the last side, AB, is going to be the biggest side because it's opposite the biggest angle. So if you got that one right, good job. So go ahead and try number 11. When you come back, we'll do it together. All right, we're back. For this problem, we're going to use something called the triangle angle inequality theorem, which says if you look at the smallest side of a triangle, the opposite angle of that side is going to be the smallest angle. And they want the smallest angle first. Then if you look at the next biggest side, the angle opposite is going to be the next biggest angle in the triangle. So angle D. And then, of course, angle E is going to be the biggest angle because it's opposite the biggest side. So if you got those right, good job. It says the polygons below are similar. So we know these polygons are similar. Use them to answer problem numbers 12 through 13. So go ahead and try 12 and 13, and when you come back, we'll do it together. All right, we're back. If these polygons are similar, then we know 2 things about them. Number 1, corresponding angles are congruent. So we can go ahead and use that to answer problem 12. So that means that x is equal to 65 degrees and z is equal to 70 degrees because they're in the same relative location. And the second thing that we know about similar polygons is that the ratios of corresponding sides must be equal. 3/7, those are corresponding sides where we know their length. So we know 3/7 must be equal to the ratios of all the other sides. But we're looking for y. So what is the corresponding side over here of y? That's going to be 6. So we get 6/y. We know these ratios must be equal. And again, I can set that equal to the ratios of everything else also. I can say that that's 2.7/b and just keep going and going. But we're not solving for b in this problem. We're just solving for y. Now, please understand that if you flip this, flip that fraction and you write this proportion here, this statement, that's not correct. Or if you write 3/7 is equal to y/6, that's not correct. If your numerator is the smaller number, meaning it's bigger than 7, so we got that from here, then your numerator over here must be the smaller number. We have to get that from the same polygon. And your denominators are the bigger numbers, comparatively speaking, because this is the blue is a bigger polygon. They have to be the denominators. The blue have to match up and the yellow have to match up. If they don't, you're going to get the wrong answer. At this point, we have to solve this proportion. This is called a proportion when you have two fractions equal to each other. Now, I want you to be aware that a lot of students have a lot of trouble solving these basic equations. And it's not really their fault that they have problems solving these basic equations. The reason that students have so much trouble is because there's like 6 different ways to solve this equation, and teachers will teach one method, but then when another teacher down the line, maybe 6 months later or 2 years, 3, 4 years later, shows you how to solve this, that teacher will use a different method and confuse you. So which method do we use? It just depends on which method you learned. The reason that this equation can be difficult for students is the variables in the denominator. But I'm going to try to solve this the way that we solved it in my beginning algebra course. So what I'm going to do is get a common denominator here. So I'm going to multiply both sides of this fraction by y. So we get 3y. In fact, I'm going to show what I'm doing here. This is just the way that, this is not the fastest way to do it. This is just the way that I showed how to do it. It's the easiest way to understand, theoretically. So I'm going to multiply both sides of this fraction by y, and I'm going to multiply both sides of this fraction by 7. And so now we get 3y over 7y is equal to 42 over 7y. So we have two fractions that are equal to each other. Again, that's called a proportion. And notice that the denominators are the same. If the denominators of those fractions are the same, then obviously the numerators must be the same. So I'm going to try to shrink this stuff. So then we end up with 3y is equal to 42. And if we divide both sides by 3, we get 14. So y is equal to 14. So that was a very, very slow method. There's faster ways to do it. But again, I don't want to confuse you by showing you a bunch of different methods. Typically what students do is they just kind of have a meltdown. They just think, I don't know how to solve it. I can't remember how to solve it. Well, you're now in a geometry course, which is technically a 10th grade course. It doesn't matter how old you are, if you're 5 years old or you're 50 years old. Just figure out how to solve it. Okay, that is an easy problem compared to the stuff that you did in my beginning algebra course. That is very, very simple. So just play around, try some different things. You can flip both sides of the equation, so you end up with y over 6. Then you multiply both sides by 6, and the 6's cancel out, and you have y is equal to whatever that is. You can also use cross multiplication. So 3 times y is equal to 7 times 6. There's so many different ways to do it. And I told you I wasn't going to show you all those ways, but there I go showing you. So a lot of different ways to solve those. Try part 2 if you haven't already tried part 2. It's the same situation with part 2. When you come back, we'll do it together. All right, we're back. So I've got these green sides. 3/7. Again, the ratios of corresponding sides must be equal to each other. So 3/7 must be equal to 2.7 over b. And if we use the same method that we used before to solve this, we multiply both sides of this equation by b and both sides of this equation by 7. Trying to look for different colors here. Multiply both sides of that fraction by, not the equation, the fraction by 7, and we get 3b over 7b is equal to, and here's where our calculator comes in handy. 2.7 times 7 is 18.9 over 7b. So we have two fractions that are equal to each other, and the denominators are equal to each other. So those denominators are equal to each other, which means that the numerators must be equal to each other. So that means that 3b must be equal to 18.9. That's kind of just common sense. So now, again, we're going to need a calculator. You're not really required to do that in your head or on paper. So divide 18.9 by 3, and we get 6.3. b is equal to 6.3. Now there is kind of a fast method to do that. Actually, with this strategy, it's probably better to just use a calculator. Okay, so if you got that answer, good job. On to number 14. So try number 14. When you come back, we'll do it together. All right, we're back. We're going to have to use the triangle proportionality theorem, which tells us that if there's a line or a segment or a ray or something that is parallel to one of the sides of a triangle, then that segment or line or ray or whatever divides the sides of the triangle proportionally. So what that means is 6 over x, these two numbers here, is equal to 9 over 6. Now you could also write x over 6 is equal to 6 over 9. That's actually better because that's easier to solve. But I already wrote that first one, so I'm just going to keep it there. You always want to deal with small numbers if you can. So divide both of these numbers by 3 and you get 3 over 2. And again, now we have a proportion. So this is a point of contention for a lot of students. A lot of different ways to solve this. But using the method that we learned in my beginning algebra course, you're just going to multiply both sides of this fraction by 2 and both sides of this fraction by x. And we get 12 over 2x is equal to 3x over 2x. And notice that the denominators are the same. So what that means is that the numerators must be equal to each other. Now we're out of room, but that means don't panic. We can just go up here. So 12, the numerator there, must be equal to 3x, the numerator on the other side of the equation. Divide both sides by 3, and we get x is equal to 4. So if you got that answer, good job. Go ahead and try number 15, and when you come back, we'll do it together. All right, we're back. So we're going to have to use the proportional areas theorem, which tells us that if two polygons are similar, then the ratio of the areas of the polygons is equal to the ratio of corresponding sides squared. So that means that A1 over A2, that's the ratio of the areas, has to be equal to 3 over 1 squared. So if it's area, you square it. If it's perimeter, you don't do anything to this. And if it's volume, later on we're going to learn that you actually have to cube it. So A1 we know is 36. They tell us that over here, you see. And that's equal to 3 over 1 is 3. And then if you square 3, you get 9. And again, this is a point of contention for a lot of students. There's a lot of different ways to solve this problem. But what I'm going to do is rewrite 9 as 9 over 1. And again, this is not the fastest way to solve this equation. It's just the way that we learned in my my beginning algebra course. But the other fraction, we're going to multiply both sides by A2. And we're out of room, but that's okay. Don't panic. Just use an arrow. So now we end up with 36 over A2 is equal to 9 times A2 is 9A2, and 1 times A2 is just A2. So now we have a proportion, two fractions that are equal to each other, and the denominators, as you can see, are the same. So that means that the numerators must be the same. So 36 must be equal to 9a. Divide both sides by 9, and you get A2 is equal to 4. But remember, you have to use units for these problems. Area in this particular problem is going to be in square inches. You must write square inches or you're going to lose points. You're going to miss some points for not writing the units. Okay, so on to number 16. So attempt number 16, when you come back, we'll do it together. All right, we're back. So in this problem, we're going to use the transversal proportionality theorem, which says that if three parallel lines intersect two transversals, then they divide the transversals proportionally. So that's a lot of fancy talk, but what that means is that 4 over 2 is equal to 3 over x. And 4 divided by 2, dividing these numbers both by 2, we get 2 over 1. Again, I'm taking this step by step. You can do this more quickly. So then we're going to, again, using the method we learned in my beginning algebra course, we're going to multiply both sides of this fraction by x, and we end up with 2x over x is equal to 3 over x. So that means that the numerators must be equal. So 2x must be equal to 3. Divide both sides by 2, and we get x is equal to 3/2. So if you got that one right, good job. I'm going to put a divider here. Try number 17, and when you come back, we'll do it together. All right, we're back. So now we're going to have to use the angle bisector theorem for triangles. If a ray bisects an angle of a triangle, or in this case a segment, then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So what that means is that 5 over 4 must be equal to b over 13. And, you know, we could use the previous method, but it's so much easier just to multiply both sides by 13. It's just one step, because that's going to cancel out the 13, and you're going to end up with b is equal to Now that's 13 over 1 times 5 over 4. Just multiply straight across. 5 times 13 is 65. 4 times 1 is 4. And you can just leave it like that. I'm not going to require you to change that into a mixed number. Even though in the real world you probably would change that to a mixed number or a decimal. So if you got that one right, good job. Okay, and now we're going to use the triangle proportionality converse theorem, which says the opposite, obviously, of the triangle proportionality theorem. The triangle proportionality theorem tells us that if you have a segment or array that's parallel to one of the sides of a triangle, then that segment or array divides the sides of the triangle proportionally. That's the triangle proportionality theorem. But the converse says that if these sides are proportional, they're divided proportionally, meaning if 10 over 4 is equal to 8 over 3, that proves that this segment here is parallel to this side of the triangle. So we have to figure out if this proportionality statement is true. So if we reduce 10 over 4 to 5 over 2 by dividing both sides of the fraction by 2, we see that that is not correct. So the answer is no. TU is not parallel to RS. So if you got that one right, good job. Okay, on to number 19. In the following problems, write two-column proofs showing that the triangles are similar. So we're going to show that this triangle here is similar to the bigger triangle that includes the smaller triangle. So I'm going to take those triangles out and put them over here. So that's the purple one I drew. You don't really have to color these in, but maybe this will help. So let's label the size. That's BDC. Now I'm going to label the bigger triangle. You don't have to draw these triangles, but this may help visualize what's going on here. So this triangle is AEC. So we have to prove that the purple triangle is similar to the blue one. Now we have some theorems to do that. First of all, we have the AA postulate, we have the SAS theorem, and the SSS theorem. Now be aware that these are similarity theorems and postulates. We're not talking about congruence. For congruence, you have the SSS, SAS, ASA, and AAS, and also for right triangles you have the HL. That's for congruence, but for similarity you only have these three here. And for these, obviously you're talking about the sides being congruent and the angles being congruent, but over here you're not necessarily talking about congruence for all of these. When you're talking about the angles, they are going to be congruent, but when you're referring to the sides, you're talking about proportionality. The ratios of the sides must be equal. So it's a different ball game when it comes to similarity. And we only have these three for similarity. So we can't use these theorems. And by the way, the AA is a postulate, and the yellow ones are theorems. We can't use these yellow theorems because we don't have any sides of this triangle. We're not given any information about the sides. So we're going to have to use AA to show that the purple and the blue triangles are similar. So what we have to do is we have to show that there's two pairs of angles that are congruent. So how are we going to do this? Well, first of all, we have some given information. The picture tells us, it's given in the diagram, that BD is parallel to AE. That's what those arrows mean. Now, if BD is parallel to AE, that's going to tell us some information about this angle and this angle, and this angle and this angle. And you probably already guessed it, it's going to show that those angles are congruent. But how do we know that? Well, we have two parallel lines cut by a transversal. So corresponding angles are congruent. So these are both upper left angles when you're referencing those points of intersection. The points of intersection being these red points here. The pink is in the upper left in both those areas of intersection. So we can say that angle BDC is congruent to angle AEC. And that is the corresponding angles postulate. So what that means is that angle D is congruent to angle E. You don't have to use three-letter notation for angle E, but for angle D here, you do have to use three-letter notation. In fact, I'm going to go ahead and change that to just angle E just to make it easier. We have to base our notation off this first triangle here. We don't want to confuse the reader. I know that's a little confusing there, but anyway, now we could say the same thing over here. We could say that this transversal goes through, actually let me color these. So these two parallel lines have a transversal going through them here, and therefore this angle is congruent to this angle by the corresponding angles postulate also, because they're both in the upper right direction in reference to the intersection points. But it's easier just to say that angle C is congruent in both of them, you see. Angle C is congruent in the purple triangle and the blue triangle. The blue being, again, the overall triangle, and the purple being the smaller triangle here. So we can just say that angle C is congruent to angle C by the reflexive property of congruence. So there's two ways to do this problem. One way is you could just use the corresponding angles postulate. In fact, I think I might just do it that way, because then we'll only need three steps. So angle BDC is congruent to angle E, and we can say that angle CBD is congruent to angle A. Again, there's a lot of different ways to do it. So then we just erase this red arc because we didn't use that one. We only need two angle pairs. I'm just showing you the different ways to do it. So we showed that angle B and angle A are congruent, but we use the three-letter notation for angle B. So we showed that these angles are congruent. We showed that these are congruent, and then we showed that these are congruent, and so that's all we have to do. That's the AA similarity postulate. So now we can say that triangle CBD is similar to triangle CAE, and that is the AA similarity postulate. So if you got that one right, good job. And this is the purple triangle, and this is the blue one. Again, you don't have to use colors. All right, on to number 20. Go ahead and attempt 20. Remember, we have three things that we use to try to show that triangles are similar. So you're going to use one of these. And remember, when we're referring to the sides, we're talking about ratios being equal, not sides being congruent. So go ahead and try number 20. When you come back, we'll do it together. Prove that these two triangles are similar. All right, we're back. So we have a lot of given information. We know that FG is equal to 9. GH is equal to 21. FH is equal to 25. IJ is equal to 4.5. JK is equal to 10.5, and IK is equal to 12.5. And that is given in the diagram. We have to prove that they're similar using one of those theorems. Obviously, we're going to use the SSS similarity theorem for triangles. So we have to show that the ratio of all the corresponding sides of the triangles are equal, and then we're done. That's how this problem is done. Okay, so FG over the corresponding side in the other triangle, IJ, is equal to 9 over 4.5. And GH, and I know that just because I used substitution, GH over JK is equal to 21 over 10.5. And FH over IK is the last ratio. FH over IK is equal to 25. Let me shrink this a little bit. FH over IK is equal to 25 over 12.5. And again, we just substituted numbers in there. So if we use simplification, we see that 9 divided by 4.5 is just 2. And 21 divided by 10.5 is 2. And 25 divided by 12.5 is also 2. And that, again, is just simplification. So then if we use the transitive property of equality, then we see that the ratios must be equal to each other, and that's it. We're pretty much done. That's what the SSS similarity theorem for triangles, that's what it means, is that if the ratios of corresponding sides, all three corresponding sides, are equal, then that proves that the triangles are similar, that information alone. So now we know that triangle FGH is similar to triangle IJK. And because we started with F, the bottom left vertex, we have to start with I, the bottom left vertex in the triangle at the right, and then we went up to G, so we have to go up to J at the triangle at the right, so on and so forth. And we use the SSS similarity theorem for triangles. So if you got that one right, good job. Okay, on to number 21. If the segments below are the medians of the triangle, find the quantities listed. So we can't do this problem. It's impossible. Unless we remember what a median is. We're told that these orange segments are medians. A median starts at a corner of a triangle and goes to the midpoint of the opposite side. So that allows us to answer the first question. They want to know, what is this length over here? Well, if this orange segment is a median, then it goes from a corner and hits the midpoint of the opposite side, so that means that this length here must be 7 also. Because again, that purple point is the midpoint of BA. So BE is equal to 7. Very easy. Now we need to find BD, and to do that we need to go to the centroid theorem. Now these 3 orange segments are concurrent. How do I know that? Because there's 3 of them and they're going through the same point. They're intersecting at that same point. And the centroid theorem tells us that the medians of any triangle are always concurrent, meaning they intersect at one point. And the centroid theorem tells us that this length here is double this length. There's a lot of different ways to say that, but we can say BD is equal to 2 times, and you don't really have to show the work here, but I'm going to say 2 times FE, which is equal to 2 times 6, because we know FE is 6, and therefore the answer is 12. I'm going to write that over here. So most of these problems are pretty easy if you remember the theorems. Okay, AC, they're looking for this length here. Now again, these orange segments are medians, so they start at a corner and go to the midpoint of the other side. So if this is the midpoint of side AC, that means if this side is 10, or this segment is 10, then this segment must be 10 also. So if you add those up, you get AC, which is 20. All right? So I guess you could show a little bit of work there. You don't really have to show any work on these problems. You can just plug the numbers in. But I'm just trying to show you what's going on here for your benefit. And that simplifies, of course, to 20. Okay, it says if ED is equal to 7, find DC. So ED is equal to 7, and it wants us to find DC, this length here. So again, the centroid theorem tells us that this length here is double this length. That's true for all the medians. DC is equal to 2 times ED, which is 2 times 7, because they told us ED is 7, so the answer is 14. So if you got that one right, good job. There are 4 parts to that problem. So now on to 22. If point D is the orthocenter of the triangle below, find the quantities listed. So go ahead and try number 22, and when you come back, we'll do it together. All right, we're back. So this problem can be a little confusing for students when you're dealing with the orthocenter, that is. We're told that D is the orthocenter. Now, I want to explain something very important. Let's say that you set a triangle so that its base is like so. The height of the triangle would obviously be this little segment that goes from the very corner of the triangle to the bottom, and it has to be perpendicular to the base. And that's just the way that you figure out the height. That's the way the height is defined. Now I can turn this side into the base and flip the triangle around. Then I have something like this. Doesn't look exactly the same, but you get the point. Then the height would be this line, which again must be perpendicular to that new base. So the point I'm trying to make here is that the altitudes, whatever you want to call them, heights, altitudes, they always go through a corner of a triangle. If you drew the third altitude, that would go through this corner over here. So we know that we're not really told anything about these orange segments, but we do know that, for example, this orange segment here, it goes through this corner of the triangle, and it goes through a point that we're told is the orthocenter. Now, the orthocenter theorem tells us that all the altitudes of a triangle are concurrent, meaning they all hit at this point we call the orthocenter. So if these segments are going from corners of triangles to the orthocenter, that proves that all these orange segments are actually altitudes or heights, whatever you want to call them, of the triangle. This obviously looks like a height, but we needed all that information to prove that it is a height. Now you're probably thinking, who cares? I mean, why do we care about that? Well, the first problem is asking us to find the measure of angle BEA. And now that we know that AE is an altitude, we know that this angle here must be 90 degrees. I mean, if it's a height of the triangle, if it's an altitude, remember, altitudes are always perpendicular to one side of the triangle. So we know the answer to the first part is 90 degrees. Now we want GAF. So GAF is this angle here. We're looking for that big angle in there. You see, let me get a color here. You see this blue angle in here? They're looking for that angle there. This is kind of a tricky one. What we're going to need to do to find that angle is we're going to need to analyze this right triangle here. So I'm going to take that triangle out and put it over here. And I'm going to label this A and F and B. And hopefully that'll help you to see what's going on here. So we know that this angle is 26 degrees. And we know that this orange segment here is an altitude because it's going through the orthocenter and a corner of the triangle. So what that means is that because it's an altitude, this must be 90 degrees. That's true of every altitude. It must be perpendicular to one of the sides of the triangle. So that means that this angle here is a right angle. So that's how we're going to find the measure of GAF. And by the way, this point here is called G. That's why we're trying to find GAF. So we can say 26 degrees plus 90 degrees plus the measure of angle GAF, which is what we're looking for, is equal to 180 degrees using the triangle sum theorem. Then we get 116 plus measure of angle GAF is equal to 180. Subtract 116 from both sides, and we get 64 degrees. So there you go. Okay, so now we're going to find BD. In order to find BD, we have to analyze this triangle here. Notice we know two sides of that triangle. And we also know that this angle is 90 degrees, again, because these orange segments are all altitudes. So I'm going to take that triangle out and draw it down here, just so we can see what we're dealing with. I want to try to write it so it kind of looks like the triangle, obviously. And we're looking for BD. So obviously we're going to use the Pythagorean theorem because one of those angles is 90 degrees. So 5 squared plus 12 squared is equal to BD squared. 25 plus 144, and again, you have your calculator. Don't be afraid to use your calculator. You're allowed to use your calculator on the test, as long as you're not using some crazy advanced calculator. We're going to square root both sides because we're not looking for BD squared, we're looking for BD. So we're going to square root both sides. Whenever you do that, we add a plus or minus. Again, you can use your calculator. And we get plus or minus 13. But it's impossible for the side length or any kind of length to be a negative number. So it's got to be positive 13. So if you got that one right, good job. So now we're going to find the measure of angle AGC. And again, these are all altitudes, these orange segments. So that means that this angle here has to be 90 degrees. AGC is 90 degrees. There's no work that's really required for that problem. So 90 degrees. If you got that answer, good job. On to 23. Go ahead and try 23, and when you come back, we'll do it together. All right, we're back. If point E is the circumcenter of the triangle below, find the quantities listed. The circumcenter is generated when you draw all the perpendicular bisectors of a triangle, because all the perpendicular bisectors are concurrent, and that means that they hit at the same point that we call the circumcenter. For this problem, as in the previous problem, we're not told that these orange segments are perpendicular bisectors. But we do know that they're perpendicular to the sides of the triangle because those red boxes, and we do know that they all go through the circumcenter because the problem tells us that that point E is the circumcenter. So because they're perpendicular to each side of the triangle, and because they're going through the circumcenter, that proves that they must be not only perpendicular to the sides of the triangle, but also bisectors of the sides of the triangle. So if we know AF, then we know FB. They're the same length. So 5 2/3 is FB. If you got that one right, good job. EC. In order to find EC, we have to know the circumcenter theorem, which tells us that the circumcenter is equidistant from the vertices of the triangle, or the corners of the triangle, whatever you want to call them. So if this length here is 10, that means that this length must be 10 also. So again, if you know these theorems, the math really is not difficult. You can answer these problems very quickly. All right, part 3. If HE equals 8, find CH. So they're telling us that this length here is 8. So how do we do this? Well, we have to kind of treat it as a puzzle. It's a tricky problem. What we're going to have to do is we're going to have to consider this triangle over here. You may not see that immediately, but that's okay. Just look around, see if you can find some triangle or something to figure out how to do this problem. So what I'm going to do is I'm going to take that triangle out and put it over here so we can see what triangle we're dealing with. And that's C, E, and H. Now, remember, we figured out that this side is 10. We already figured that out. That's EC, that's 10. And we're told in this problem that HE is 8. So that's 8. And obviously, if this angle here is a right angle, then this angle would also be a right angle. You see that? Because the linear pair postulate. You see, this purple side here is obviously a straight segment. So these two angles, the purple angle and the blue angle, they must add up to 180 degrees. So if that red box is 90 degrees, then this angle must be 90 degrees also. Okay, so that's a 90-degree angle, and so obviously we're going to use the Pythagorean theorem. So let's say 8 squared first. Let's do the legs first. 8 squared plus HC squared is equal to 10 squared. So 64 plus HC squared is equal to 100. Subtract 64 from both sides, and you get 36. We don't want HC squared, we just want HC. So square root both sides. To get rid of that square, you have to write a plus or minus whenever you square root both sides of an equation. What number times itself is equal to 36? Well, that's just going to be 6. But remember, a length cannot be a negative number, so it's going to be positive 6. So there you go. We found it. All right, so if you got that answer, good job. Now for BC, we just found, well, actually we just found HC. which is 6. HC is 6. And remember, we discovered that those orange segments are perpendicular bisectors. So that orange segment there bisects this side. So if HC is 6, then BH must be 6 also. And if you add those two up, we get BC, which is what we're looking for, which is 12. BC is 12. 6 plus 6 equals 12. And I should say maybe, well, that I don't think I really need to write more than that. Okay, so if you got that right, good job. On to number 24. So it says we're going to find the coordinates of the orthocenter of the triangle below. Now, I want to warn you that when you're trying to find the coordinates of a point of concurrency, if you notice that the triangle is a right triangle, oftentimes you can see that this is going to be a much easier problem than you might expect. And because we're dealing with rectangular coordinates here, meaning x and y and so on and so forth, then we can see that this is a right triangle. This is a 90-degree angle in here because this line is going straight up, or that side is going straight up, and this side is flat, horizontal. So the reason that makes this problem easy is because, remember, orthocenter is the point where all the altitudes of the triangle, or the heights of the triangle, they meet at that point. So an altitude of a triangle starts at a corner and goes to the base, but the base is this side. So that altitude is just going to go straight down like so. And here, if you consider this corner to be the height of the triangle and this side to be the base, then you can see that this side here would be the altitude. So those two segments, they both meet at the orthocenter. So in this problem, you don't really have to do a lot. If you want to show some work, we could say the line containing altitude, we'll call it altitude 1. That is going to be x is equal to -2. Now, where did that come from? Remember, if you're drawing the equation or writing the equation of a vertical line, you just figure out where that vertical line is on the x-axis. It passes through -2. The x values are always -2, so that's the equation of that vertical line. And then the line containing altitude 2, we'll just number it 2. That's going to be y is equal to, and you see this flat line, the y values are all at 1. So that's the equation of that horizontal line. So obviously they're going to meet at the same point. So the point of intersection is going to be -2, 1. There's not really a lot of work you have to show on that. So remember, if you have a right triangle on these problems where you have to find the coordinates of a point of concurrency of the triangle, sometimes you can answer that problem pretty quickly without a lot of work. In fact, I don't even really require you to do this stuff. You can just write the answer. All right, if you got that one right, good job. Now this problem is going to be more involved because this is not a right triangle. And be aware that even if you do have a right triangle, if the right triangle is orientated in a way that's not easy to see it's a right triangle, you may not be able to use the method that we used previously. So it says find the coordinates of the circumcenter of the triangle below. Now the circumcenter is generated by drawing the perpendicular bisectors. So this perpendicular bisector would be about here. It's perpendicular to that side and it bisects that side. And if we draw the perpendicular bisector of this side here, then it would look like something like this. So you can see that the perpendicular bisector is probably going to be somewhere around there. So again, it has to be perpendicular. It's not exactly perpendicular, but I tried there. And it has to bisect, has to be at the midpoint of that side. So we're going to find the equation of those two lines and then set them, find the intersection of those two lines by solving that resulting system of equations. And you can use these two sides, or you can use these two sides, or you can use these two sides. It doesn't really matter, whatever is easier. So we're going to start with the line containing perpendicular bisector 1. I'm just going to call it 1. And so that's going to be this one here. So I'm going to draw that. And I'm going to label that PB1, perpendicular bisector 1. All right. So there's two things that we need to do. Again, we're finding the equation of the equations of two of these perpendicular bisectors. So we're starting with the first equation here. There's two things that we need to write the equation of a line: slope and a point. So to find a point, all we have to do is find the midpoint of these 2 points here. So the midpoint of D and E is just the sum of the x values divided by 2. That gives you your x coordinate. And then you add up the y values, which is 5 plus -1, and divide by 2, and that gives you the y coordinate. So simplifying that, we get the midpoint. And again, this midpoint is here. That's that point there. Maybe I should keep the colors. So then we get capital M DE, that would be -1. 0 plus -2 is -2. -2 divided by 2 is -1. And then 5 plus -1 is 4. 4 divided by 2 is 2. So the midpoint there is 2. So I'm going to go ahead and label that. That is -1, 2. So now we have a point on that perpendicular bisector 1, that pink line. But now we have to find the slope of the pink line. To do that, we're going to find the slope of this side of the triangle, and then we're just going to find the opposite reciprocal. Because remember, if you have one line that is perpendicular to another line, and you know the slope of the first line, the slope of the perpendicular line will just be the opposite reciprocal. So this first part of the problem we can just label as part A of that part. And part B, we're going to find the slope of DE, which is 5 minus -1 over 0 minus -2. So be very careful because those are double negatives. So we get 5 plus 1 is 6, and 0 plus 2 is 2, which is 3. So that's the slope of DE, but we don't want that slope, okay? We don't want the slope of this side here. We want the slope of the perpendicular bisector, which is perpendicular. So the slope of the line we're looking for, that's perpendicular, so we take this and flip it and change the sign. So consider this to be 3 over 1. You flip it, it's 1 over 3, and change the sign. So that's the slope that we're looking for. So now we're ready to write the point-slope form of our line because we have a slope and a point. And so the point that we have is -1, 2. So I'm going to plug in 2 there. So that 2 came from up here. And the slope is -1/3. That slope came from there. And the x value of our point is -1. And that came from up here. So now we have y minus 2 is equal to -1/3 times x plus 1. And to simplify this a little bit, I'm going to put it in slope-intercept form. So I'm going to distribute the -1/3, use the distributive property. And then I'm going to add 2 to both sides. So we have -1/3 x. And 2 plus -1/3 is going to be 5/3. So there you go. That's what we're looking for, the equation of the line containing perpendicular bisector 1, that pink perpendicular bisector. So now we're going to move on to the line containing what we're going to call perpendicular bisector 2. So let's draw that, what that would look like. So it has to be on the midpoint of this side and has to be perpendicular to that side. So it's going to look something like this. Not exactly, but something like that. It's not exactly perpendicular, but you get the point. All right, so that's perpendicular bisector 2. And we're going to do the same thing. We're going to find the midpoint. We need a point on the line, and we need a slope of the blue line. So we need a point on the blue line and the slope of the blue line. So a point on the line is going to be found by discovering the midpoint of the segment DF. So we add the x values and divide by 2, and we add the y values and divide by 2. And you come up with 0 plus 4 is 4, 4 divided by 2 is 2, 5 plus 1 is 6, 6 divided by 2 is 3. And I'm going to move this stuff over. And we can put dividers. Don't be afraid to put dividers for your work. It makes it a lot easier for the reader and for you. So that's the point. I'm going to draw that point. It's 2, 3. And now we're going to find the slope of DF. The slope of DF is 5 minus 1 over 0 minus 4. So that's 4 over -4, which is -1. But we don't want the slope of DF. We want the slope of the blue perpendicular line. So that's going to be perpendicular. So you take this, which is -1 over 1, and you flip it, and you get same thing, but we're going to change the sign so it becomes +1. All right. So we have a point on the blue line, and we have the slope of the blue line, because we know the blue is perpendicular to DF. So now I'm going to use the point slope form again. Y minus 3 is equal to the slope, which we just found is 1, times x minus 2. Now where did I get all that? I got the 2 from there, and I got the 3 from there, and I got the 1 from there. So now we're going to change that to slope-intercept form. So we have y minus 3 is equal to x minus 2, multiplying 1 by all that stuff in the parentheses doesn't really change anything. And then add 3 to both sides, and we have x plus 1, so that is the equation we're looking for. So now we're ready to find the intersection point. And that the intersection point is going to be the circumcenter. So in order to do that, we develop a system of equations. One equation is the equation we just found, and the other equation is -1/3 x plus 5/3, and we can join those with a brace. So what we can do is we can take all of this stuff here, which is equal to y, and just throw it in for y on this equation. That's called substitution. So I'm going to go ahead and do that up here because we're kind of out of room. Again, don't be afraid to use dividers. So that gives us negative 1/3 x plus 5/3 is equal to x plus 1. And I'm just going to change this to 3x over 3 plus 3 over 3 is equal to negative 1/3 x plus 5/3. And again, if you consider these to be over 1, I'm just multiplying both sides of this by 3 and then multiplying both sides of this by 3. That's just the fundamental principle of fractions. There's a lot of different ways to solve this equation. Easiest way is actually just to multiply both sides by 3. So at that point, and I'm going to change this to negative x over 3, we can add them up and we get negative x plus 5 over 3 is equal to 3x plus 3 over 3. So we have two fractions that are equal to each other. And as you can see, the denominators are the same. They're both 3. I'm going to find some more room here. So the numerators must be equal. Then we add x to both sides and subtract 3 from both sides. Divide both sides by 2, and we get 1/2 is equal to x. So now, in order to find y, we can just take this equation over here and rewrite it. So we have y is equal to x, which is 1/2, plus 1, which is equal to 1/2 plus 1 is 3/2, or 1 and 1/2, however you want to write that. So the intersection point, our final answer, is 1/2, 3/2. So that's the final answer. So if you got that, good job. You can do that a lot faster than I did it. I was just trying to, explain every single step. Remember, when you do the test, you don't have to explain every single step. So you're going to go a lot faster. Okay, take a screenshot here. If you want to take screenshots of all the work that we did to help you with your homework or to study for the test, go ahead and do that. And I'm going to require you to do that at this point because you're studying for the test. In fact, I'm going to require you to look at all the screenshots of all the classwork we did in the last 2-3 weeks, however many weeks it's been since we started in the third part of the course. So again, you're getting screenshots here. And last screenshot of the classwork, but don't go before you get your practice test. Remember, you're going to do a practice test. So here is the practice test that you're going to do for homework. Here's screenshot number 1 and screenshot number 2 and screenshot number 3 and screenshot number 4 and screenshot number 5 and screenshot number 6 and screenshot number 7. But don't go before you get your answers. Remember, it's not enough just to attempt the practice test. You have to get the right answers, do it correctly and completely. So here's screenshot number 1 of the answers for your homework, the practice test version 2. And here's screenshot number 2. So get that practice test done completely correctly and neatly and put it in order in your binder. And remember, if you don't study for that test and get these practice tests done, the one that we did together just now and the one you're going to do for homework, then there's a very, very little chance that you're going to pass test number 3. So get that practice test done, and I'll look forward to seeing you in the next class.